Oopsies. Oh, my little sketchy setup here. Okay, so today we are going to start talking about chemical kinetics. Okay, so nobody ever knows what this word means. Kinetics is the study of reaction rates. I have on my page a full sheet and then like half, but I wrote really small like over here that I could have put here. So like a page and a half. It's pretty spread out though. All right, so kinetics is the study of reaction rates. What's a rate?
How fast something goes or doesn't.
That's correct. So what you're talking about in chemical kinetics is really the speed of a reaction. Some reactions occur very quickly. The reaction of sodium metal with water is very quick. It happens almost instantaneously, and almost all of it reacts instantaneously. Other reactions take a very long time to progress. Like for example, the chemical reactions that are happening in all of our bodies right now, like the aging process, those are all pretty long processes that don't happen instantaneously. Otherwise, we would just be old people in young people bodies. So chemical kinetics is important for us to study because if we need something to happen quickly, we need to know how our chemical reaction is going to be affected by different things. Okay, so there are three factors that affect the rate of a reaction, or how fast or how slow how fast or how slow a reaction takes place. The first factor is concentration. All three of these factors are pretty self-explanatory. So if you have a greater concentration of reactants, if you have more reactants, do you think that your reaction will happen faster or slower?
Slower.
If you have more reactants, it'll happen faster. Higher concentration equals higher rate. Okay, so the best example I can think of for concentration is if you have, if we got 100 people in this classroom. Oh, did we talk already about lockdown?
No.
Okay, so it could be, we just got to get all the lights out. So we just have to unplug the shit. So if that happens today, then we just got to unplug the things. Okay, so let's say that we put 100 people in this classroom with the desks and the lab benches and everything. And we blindfold everybody and we tell everybody to just walk. Every time a chemical reaction happens, it's like represented by two people colliding into each other. If we have 100 people in this classroom, it would happen pretty fast that somebody was colliding with another person, right? Because there would just be so many people in here. Versus if just the 7 of us right now put blindfolds on and we started walking around, it might take a while for any of us to bump into anyone else. So the more reactants you have, the faster they will probably, they're just more likely to interact. Remember that in order for a reaction to happen, molecules must collide. So this, like, collisions molecularly aren't as catastrophic as, like, let's say if you're my mom when she gets in her car. I mean, a collision is bound to happen at some point. But you think of normally when you hear the word collision as, like, destructive. In chemistry, we don't mean that. We just mean that they are in proximity, that something can happen with their electrons, that a bond can either be broken or made. It just means that they come in contact with each other. The second factor that affects the reaction rate is the temperature of the reactants. So for the most part, if you increase temperature, what you're doing is you're increasing the speed of the individual molecules themselves. You're increasing the energy of your particles. And so now if you can imagine the example of us walking around the room with our blindfolds on, if we're all running, the chances that we will collide with someone else increase because we're just moving at a faster speed. So an increased temperature is equal to a rate increase as well. This is something you, temperature is something that you already have experience with probably. If you've ever tried to make hot chocolate, like with the packets, and you first like take your cold water, your cold milk, and try to put the hot chocolate packet in and like stir it up. There's always that like little bit of crusty crust on the top, right? Because not everything dissolves into the liquid. But then after you heat it up and you give it a nice stir, then it does dissolve in, the reaction happens. And that's because your temperature has increased, the molecules have greater energy, so they're able to form a reaction better. And the final factor that affects the rate of a reaction is the surface area of reactants. The greater the surface area, the greater the rate. So another cooking example, if you have to melt a stick of butter, you can put the whole stick of butter in your saucepan and just let it cook down. It'll take quite a bit longer for that to happen than if you were to like just chop all of the stick of butter up into little bits and toss them in there, because you're increasing the surface area. There's more of the butter that's touching the hot of the pan, and so it'll melt faster. I can speak, it'll melt faster. Same thing if you like, some people are weird and they like special kinds of ice better. So you can get like the big blocks of ice, like ice cubes, I mean, or you can get like, some people even have fancy ice makers that make like the little balls, or Quick Trip has like the little fine ice. That ice will cool your drink down faster because there's so much more surface area, so that all of those little, like, so if you can imagine in your liquid, if you've got all of these like ice balls, all of this surface is going to be touching the liquid around it, cooling it off. Whereas if you had the same quantity of ice, so if you had the same quantity of frozen water, but just in one solid ice cube, it'll take longer for that ice cube to cool down your liquid.
But it'll melt quicker.
Which will melt, no.
The smaller?
The smaller ones will melt quicker.
Yeah. Okay.
Yep. Yep. And that's how the liquid will become more cold. Okay, so now that we know the factors that affect reaction rate, we're going to do a lab on this next week. So keep track of this. I'm going to ask you, on Friday we'll prepare these experiments. I'm going to ask you to create your own experiment where you test one of these three things to prove whether or not it's true, or if you can confirm your, if you can confirm or disprove your hypothesis, I should say. So just keep a note of where you wrote that down. You'll need it later. There are two ways that we can calculate reaction rates. And both of these we learned last year. The first is the rate. This is what it's called. The rate with respect to change in concentration. There's no abbreviation for this. So what does this look like? There's also no abbreviation for rate. It's just, we use the word rate. So now, because whenever you have a rate, it's the speed at which something happens. So change in time is always the denominator of these kinds of equations. So do we remember what triangle means?
Delta.
Yep. Triangle equals delta, which is, it's capital delta in the Greek alphabet, which means change in. And the way we calculate delta is always final minus initial. Those are things that are always true. Always final minus initial.
I can't see that.
Oh shoot, I used the green. I'm sorry. Let me write it in a different color. Oh, you know what? Hang on a second. Let me try to change my background color and maybe that'll make a difference. Nope. Okay, nope.
Oh, that helped us seeing it though.
Now you can see the green, but you can't see the black. Is this better? A little bit? Better? Here's the white. Is it too bright?
No.
No? Okay. Then we'll leave it on the white. I feel like the eye doctor. You know how they always like give you the two options? Which one is better, 1 or 2? Oh, it's a little bright. Okay, that's right. I'll manage. I'll make do. Okay, so the way that we abbreviate concentration is using the square brackets. So if we were to use just a random thing, X, this would mean concentration of X, whatever compound X is. Okay, so I'm going to give you an example of what a rate with respect to change in concentration looks like. We did this last year, so this is not new. Always at the beginning, you're going to write rate equals. And you can calculate the rate for every substance in your reaction. They should all be the same thing. So for the reactants, we always start with a negative because we are using reactants up. And then we want the change in the concentration of that chemical, whatever it is. In this case, my reactant is N2O5. And then divided by whatever the stoichiometric coefficient is times change in time.
Is that a negative in front of the... Okay.
Reactants are always negative because we are using them up. So then that means that NO2 is not a reactant, it's a product. Should it have a negative sign?
Nope.
Nope, because it's being made. Now my stoichiometric coefficient here is 4, so I should have 4 times delta T. And now for my last substance in my chemical equation, the stoichiometric coefficient is 1. So I don't need to write it. I mean, you can if you want to, but don't. So what I'm saying here is that the speed at which I am using up this reactant is equal to the speed at which I am making this product and this one as well. The reason this has to be negative for my reactant is that because I'm always doing final minus initial, my final is going to be less than what I started with. So let's say I started with 5 of them and I end up with 2. 2 minus 5 is a negative number. That
is really hard to see.
Okay. The rate must be a positive number. So if you were to calculate this and see, oh, it's -3, that's bad, I need it to be a positive number, you can think to yourself, that's why this negative is here. 2 negatives make a positive. Okay, so that explains why the negative is there. Now let's explain the stoichiometric coefficient. These numbers tell us how much of a substance is either being used or being made. So what I'm saying when I write out this rate is that I'm just going to compare the two products, for example. Based on my stoichiometry, based on my balanced chemical equation, every time one oxygen molecule gets made, 4 NO2s need to be made as well. So I can't make one of this without making 4 NO2. But I need the rate to be the same number because the speed doesn't change just because I need to make more of them. And so that's why these stoichiometric coefficients are here, because that's going to be what makes the rate equal. In the same way that I need 2 N2O5 for every 1 oxygen that's created. So just because I'm saying that I'm going to produce 4 times as much NO2 doesn't mean I'm going to produce it 4 times faster. The speed at which I produce 4 and 1 is the same amount. I just need to produce 4 in that same period of time. Okay, so any questions about this? There will be some questions on your homework where you actually have to solve and figure out what the actual numerical value is for your rate. You'll need to know what your unit is for that. So if you have change in concentration divided by change in time, your unit as your numerator will be molarity, because that's what we normally use to calculate concentration. And your time unit can really be any measure of time. So it could be seconds, it could be minutes. I'm not going to write equals, I guess I should say or. It could be hours, depending on what your unit of time is. So this number is usually fixed at molarity, but your unit for the denominator can be anything. Just depends on what kind of device you use to measure. If you have a reaction that takes 10 minutes, you probably won't use seconds because you'd be dividing by 600, and that might not be a number that it makes a lot of sense. In the same way that if you had a reaction that took an hour and a half, you wouldn't use minutes maybe, or maybe you wouldn't use seconds, because that would it just gets to be too big of a number. All right, so let's take a look at what a graph of reaction rate would look like. So I'm going to do this twice. The first time I'm going to use reactant concentration here as my y-axis to show you what is going to happen to the reactant. Reactants get used up. So their reaction concentration is going to start high, and over time, it'll decrease until nothing is left. This almost always is not a linear relationship. There are reasons for that. The initial rate is the rate when the reactants first start reacting. Initial meaning the beginning. I'm going to tell you it's almost always, and what I mean by almost always, I mean like 99.99% of the time for you, the initial rate is almost always faster than any other rate. And the reason for that is because there's a greater probability of things colliding when there are more of them. So as you start moving through your reaction, the reactants get used up. Imagine that you're in the classroom with 100 people, you all have your blindfolds on, and every time you touch a person, you and that person you touched leave the room. At the very beginning, if there are 100 people in here, right away, people will start touching and then they'll leave. And so if in the first 30 seconds, 25 people touch another person, how many people have left? And now you only have 50 people. In 30 seconds, your concentration has decreased by half. But now, because there's only 50 people left in the room, the odds of running into somebody aren't as great anymore. And we know this because we just already talked about how an increase in concentration is going to make us increase our rate. The opposite's also true. So as the concentration decreases because you start using it up, you are going to slow down your rate as well. And so when you get down here to the bottom, you can see the slope of this line is getting to be pretty flat. Whereas here, it was pretty like straight up and down. I would say that last year on the homework assignment that I gave you for kinetics, almost 90% of the people did not know the answer to these kind of questions. The same thing with the exam, because they just don't think things through logically. So now that you guys are in AP Chemistry, I expect you to retain this information. The initial rate is fastest because as things react, you take them out of the population pool, the odds of reacting then are less. Okay, so the initial rate only occurs at the beginning. There are other instantaneous rates that we can determine. Have you in math land learned about how to calculate the slope of a line, like with a tangent? Okay, that's all right. That's how you calculate instantaneous rate. You like find like a tiny little bit, like so the change in as much as that, like as the tiniest time segment that you can. So you want time to be as small as possible. Change in time is small. You can calculate instantaneous rates anywhere in the course of a reaction. The initial rate is also an instantaneous rate. It just happens to be the special one that happens right at the instant when chemicals start reacting. Right when they first get poured into the beaker, that's your initial rate. But you want to find out at the instant, so you would want to try to make your measurements like as close together as possible. And then there's one final rate that you can calculate, and that's over the entire span of the life of your reaction. That's called the average rate. So in order to calculate the average rate, let's say you're using a reactant, you would use final minus initial for your change in concentration. So let's say we've got delta X divided by delta T. Your initial time, T initial, would be 0 because you're starting at, like if you say that this is 0 here. And then your X final, the concentration of X at the end of your experiment, would also be 0 because at the end of your reaction, your reactants are used up. So then final minus initial. If this is for a reaction, you still need to have that negative sign. Final minus, let's say we've got 1. And let's say it took 1 minute, so 60 seconds. 60 minus 0. And so this should be a positive number. It'll be 1/60 Your unit would be molarity per second. And that's how you would calculate rate. This is the average rate. It'll always be slower than the instantaneous, or the initial rate at the beginning. I'm sorry, you can't read that.
What does that say?
Always slower than the initial rate. The average rate is always slower than the initial rate.
Do you want this back?
Sure. You put it back. Thank you, sir. Okay, so any questions about rate with respect to change in concentration? Almost. So I told you there were two types of ways to calculate rate. This is the second one. It's called the rate law. We also learned this last year. And so if this is your pretend chemical equation, this is a way that you could calculate, or you could write down the rate law. So copy this down and then I'll explain it.
Is that K?
Mm-hmm. It's cursive K. It makes a difference.
Are we supposed to write cursive K?
Well, just know that it is.
Okay.
If you can't write a cursive K, that's not the end of the world. Okay, so what is K? K is the rate constant. And remember that a constant is a unique number that's special for each reaction. The only way that you can figure out what a rate constant is through much experimentation. So then we see that we've got A and B, and remember what that notation means. So it's the concentration of your reactants